Hey guys, welcome back to my YouTube channel. Today we're going to talk about the Grignard reaction. The way I want to structure this video is I want to talk about it in three main parts. First, I want to talk about the general formula of the reaction, which is this pink part right here. Second, I want to talk about how do you generate the reagent that's going to be involved with the reaction, which is this blue part. And then thirdly, I want to talk about a few examples of the Grignard reaction taking place in. First, let's talk about the general formula. So the general formula of the reaction is that we will have a Grignard reagent, which is going to follow this general formula, RMGX. It's going to react with a carbonyl of some sort. It doesn't have to be a carbonyl, but it usually is. And then the product of it is going to have two main things you want to point out that you want to focus on, which is that the oxygen component of the carbonyl is going to be converted to an alcohol via protonation. And then whatever the Grignard reagent is going to actually have an alcohol component to it, and whatever that might be, whatever this R is actually also going to be a part of the newly formed product. So for forming the reagent, so what we're going to have is we're going to have one of two things. We're going to either have an alkyl halide or an aryl halide. Alkyl meaning straight chain, aryl meaning it's an aromatic of some sort. Halide meaning there's going to be a halide right here. That's the X here, by the way. And you're going to react that with magnesium in the presence of ether to produce this RMGX, such that the R is the alkyl, Mg is magnesium, X is halogen, and magnesium is going to insert itself between the carbon of the alkyl group and the halide. And it's going to do this in the presence of ether. The reason why it's ether as opposed to water is because this entire reaction, both generating the reagent as well as the reaction itself down here, has to be done under anhydrous conditions, meaning you don't want water, you don't want moisture, you don't want any of that, because if you do have water, the water will mess with it because it will act in acid-base chemistry with the Grignard reagent, this thing right here, to decompose it into something you don't want. Ether also does a good job of acting as a solvent because it will control the reaction in such a way so as to orient itself around the Grignard reagent so that it doesn't react with other reactants and do something you don't want it to. So here's an example right here. Here we have, in this case, like I said, you can have one of these. In this case, it's an alkyl halide, as indicated by its straight chain structure. And then you're reacting again, like I said, magnesium, here, in the presence of ether, diethyl ether probably. And the product of this is simply the exact same thing as the reactant, plus magnesium in between this carbon and this bromine. One thing I want to note also with this is that the Grignard reagent is going to essentially act as the carbon here, which is the important part of it. It's going to act as a nucleophile because it's slightly negative, and then whatever the carbonyl is going to be slightly positive. That central carbon that's attached to the oxygen, that's going to be slightly positive, and it's going to be the electrophile, meaning electron deficient, and this is going to be the electron rich. So let's talk about these four. Here we have 4 examples of it. What's different from each 4 of these is not necessarily really the Grignard reagent. That's kind of the common theme here. What's really different is what the carbonyl is, okay? And the idea of this is that the carbonyl, the identity of the carbonyl will determine whether the alcohol component of it, this part right here, and so on and so forth, is going to be a primary, secondary, or tertiary alcohol. The reason why I wanted to include different carbonyls is because I want to show how you get either a primary, secondary, or tertiary alcohol. So let's talk about first here. Here we have, in this example, a carbonyl is a aldehyde, and the way you know that is because here you have this carbon right here, this little point right there, and then it's double bonded to this oxygen, and then here you have a hydrogen. That's an aldehyde. And so what we're going to do is, it's very simple, very straightforward. There's supposed to be here. You're going to react it here. In this case, this is the Grignard reagent in this case. All we have for the R group is simply a methyl group, so CH3. And here's your magnesium, and here's your bromine, which in this case, the halide is the bromine. All that's going to happen is that this methyl group, this alkyl group, is going to attack this, which is slightly negative, therefore nucleophile, is going to attack this central carbon of the aldehyde, which is slightly positive. And it's going to move, I should have drawn it, but it's going to attack here and form a tetrahedral intermediate structure with an alkoxide, meaning the negatively charged oxygen. And I should have drawn this looking back. It's also actually, this pi bond is going to be broken, and it's going to move, that electron is going to move to the oxygen, therefore making it negative. And then like here, like I said, this is a tetrahedral structure. Here, right here, this hydrogen is the same hydrogen here. This oxygen is the same oxygen here. The reason why it's singly bonded negative is because you had to break the pi bond to make room for this methyl group from the Grignard reagent. And then the next step is that because, like I said before, the product is going to be an alcohol, as you can see here, this is an alcohol. So all you have to do is protonate that alcohol using hydronium ions, which in this case I drew right here, oxygen, hydrogen, hydrogen, hydrogen here, H3O plus. And all that happens is, like any other protonation reaction, all that's going to happen is you're just going to protonate it. So therefore you get this oxygen, and now it has hydrogen, therefore it's an alcohol. And what I want you to note here is that in this case, this is a secondary alcohol. The way we know this is here's the carbon here that the alcohol is attached to, and it only has one hydrogen, which is why it's secondary. If it had no hydrogens, it would be tertiary, and if it had two hydrogens, only one carbon attached to that carbon, it would be primary. Here in this case, like I said before, it doesn't have to be a carbonyl. In this case, this is a case of that. Most oftentimes is though. This is CO2, carbon dioxide, reacting with, in this case, the Grignard reagent is actually an aryl Grignard reagent. Like I said before, you can have this. I'm just showing the different examples to show the variety of it. This still follows the exact same formula, which is that here's the slightly negative carbon right here attached to the MgBr, or magnesium bromide, and it's slightly negative. Here's a slightly positive carbon. As you can see, the carbon dioxide, you have oxygen here, and they're both, the oxygen is more electronegative than the carbon, therefore that's why the carbon is slightly positive, therefore an electrophile, because the electron density is going here and up and down towards the oxygens. So essentially what's going to happen is that this carbon here is going to attach at this carbon here, and it's going to add itself to each other. And in order to facilitate this reaction, this pi bond of one of the oxygens has to be broken and moved to the oxygen, which is why you see here in this product at this part, you see that one of the oxygens of the carbon dioxide is double bonded, and then one of them isn't. The one that isn't is the one that had the pi bond broken and moved to the other side. And in here, like I said before, very simple. All you have to do is the final step is you have to protonate this alkoxide component of it, so that you get an alcohol. And here, this is the carboxylic acid attached, or this is benzoic acid, because this is the benzene and this is carboxylic acid, therefore it's benzoic acid. And then thirdly, I have one more example after this. This is an ester. Ester, whenever you react an ester with in this case, this is the Grignard reagent right here. You have ethyl group right here. This is the alcohol group. Whenever you react an ester with a Grignard reagent and the Grignard reaction, here you see something a little different from these other examples, which is that you'll actually have 2 units of the alcohol, or 2 units of Grignard reagent that's going to react with 1 unit of the carbonyl, again the carbonyl being the ester. And what essentially is going to happen as a result of that is you're actually going to have 2 of the, and you see this is a product here, you can have 2 of the alcohol components on the final product with also the alcohol. And I'll talk about why in a second. So here, it's the same thing as before, same pattern. This is a slightly negative carbon, it's attacking the slightly positive carbon here, and it's going to break the pi bond to make room for it to produce this tetrahedral intermediate. And then after this, what's actually interesting about this is that this ester group right here, OCH3, is actually a much better leaving group than this ethyl group here, which is why it's going to leave. And when it leaves, as you can see in this arrow right here, you're going to reform the double bond such that, and if you look here, if you remember what this is, such that you form a ketone, right? Ketone being, here's the carbonyl, the carbon double bond to the oxygen, and then you have a carbon here and a carbon here, as opposed to just a carbon here and a hydrogen here. If it was like a carbon here and a hydrogen here, you'd have an aldehyde like here, but no, you have a ketone. And what's interesting about this, what's interesting about reacting an ester with a Grignard reagent is that, again, you can do 2 units of Grignard reagent, therefore 2 units of the alcohol component. And again, the reason why is because the ester component of it is just such a good leaving group. And then after that, you get the ketone, and then the ketone will actually, again, like I said, it's going to react with an identical same starting reagent of the Grignard reagent. So here's, these 2 are the same, right? Or they're not like the exact same molecule in the sense that the same thing, they just have the same chemical formula. So these are like, there's 2 units of these in the same reactant mixture, if that makes sense. And so, like I said before, the exact same thing happens here. Here's the carbon of the Grignard reagent attacking the slightly positive carbon of the ketone, and then you hear the pi bond broken, move to the oxygen, and then you have this tetrahedral, like I said before. And then here, like I said before, you'll notice here again, you have 2 alcohol components right here. Here's the first one, and then the second one, which is right here, is now here and moved here at the back side. it has to move to the back of the carbonyl. And then, like I said before, the very last step is all you gotta do is protonate this oxygen. And then here, like you can see here, this is actually a tertiary alcohol. Again, the reason why it's the tertiary alcohol is as a result of this, of an ester, is that this carbon here that's bonded to the alcohol component has 3 carbon groups as opposed to 1 or 2 hydrogens. Lastly, the point of showing the example of formaldehyde, this is formaldehyde, is to show that you can also actually have a different sort of type of alcohol. Like I said before, you have primary, secondary, tertiary. This is a primary alcohol, by the way. So formaldehyde is essentially another carbonyl. All it is here's a carbonyl component, here's the carbon, double bond to oxygen, and you have actually 2 hydrogens attached to this carbon right here. And so it is for this reason that you have these 2 hydrogens that you actually end up with the primary alcohol. And so, like I said before, it's same pattern. Here you have the intermediate, protonate the intermediate. Again, the reason why this is drawn poorly, I have terrible handwriting. This is hydrogen, this is hydrogen, this is the alkyl component from the Grignard reagent. The reason why it becomes a primary alcohol is because, again, you started off with these 2 hydrogens attached to the original molecule, which is formaldehyde, and those 2 hydrogens are still going to remain with us. And I mean, that's the reason why you have the primary alcohol, I guess. And yeah, I think that's everything I wanted to cover. Bloop.